Hello, hello, and welcome back. This is our last lesson in applications of integration. Today, we're going to determine the length of a curve in the plane defined by a function using a definite integral. There are times when we need to find, well, the length of a graph, y equals f of x, on an interval ab. In order to estimate the length of the curve, we can divide the interval up into subintervals and just use Pythagorean theorem or the distance formula to find the lengths of each chord or hypotenuse and just add them all up. So for example, well, let's say hi to Jim here. Hello, Jim. If we had this curve here, and I have a variety of points here marked out, well, to find the length of this curve, I could just find the distance of each of the little pieces. So the distance formula, if you remember from geometry, the difference in the x's squared plus the difference in the y's squared, and then the square root of that whole thing, comes from Pythagorean theorem. So if we're going from 0 to 0.5, we would plug the difference of the x's and the difference of the y's into our formula, and we'd get a length of 1.0078. And then we could do that for the next interval between 0.5 and 1, and we'd get a distance of 0.80039, and then we could do the next interval, and the next, and the next, and the next, and add them all together. But of course, that's just an approximation. If we want to find the exact length of the curve, we would need to take smaller and smaller and smaller and smaller intervals, in fact, an infinite number of them, which of course is leading us to an integral. So here's a curve, and I want to find the length of that curve from A to B. Now, if I just take a little tiny section of the curve, I have on the bottom of this little triangle a change in x. I also have a change in y. And the hypotenuse of that triangle, that's what I'm really interested in, is a change in L. And the distance, or the change in L, we find using the distance formula. So the square root of dx squared plus dy squared. And I just want an infinite number of those little guys. So L, or arc length, is the antiderivative of all of those little dLs. But I can't have it in terms of L. We need to have it in terms of x and y. Now, normally, when you see an integral expression, we've got some sort of a function, right, followed by a dx. Well, let's see if we can rearrange this guy to look like this, okay? So I'm going to factor out, kind of, a dx squared. So that looks a little scary, but I just factored out a dx squared and put it on the end there. And you can see if I distributed it back in, I would be back to where I started. Now, what do you notice about right in here? dy dx squared. Well, what's dy dx? That's the derivative of my function. So if I simplify this, I get the square root of 1 minus the derivative of my function, and then the square root of dx squared is just dx. Now that's something that we're used to looking at. So in general, this is the formula you use. So if you're in terms of x, you use x bounds, and then it's just the integral of the square root of 1 plus the derivative squared dx. If you're in terms of y, it's the same thing. We've got y bounds, but it's the square root of 1 plus the derivative of the function in terms of y squared dy. So let's practice this. Find the length of the curve. F of x equals 4 root 2 over 3, x to the 3 halves minus 1 over the interval 0, 1. So they've provided us with our bounds. And based on our formula, the first thing we need to do is find the derivative of our function. So we can do that just using the power rule. And we can clean that up a little bit. The 3's cancel out. The 4 over 2, we can reduce that fraction. And so our derivative is 2 root 2x. And we just plug that into our formula. So we're going from 0 to 1, and we've got the square root of 1 plus the derivative squared dx. Now we can clean that up a little bit more, and we would get the square root of 1 plus 8x dx, so that's great. And then maybe a little bit of u substitution to solve this. So u equals 1 plus 8x, du equals 8 dx, 1/8 du equals dx, and then we can change our x bounds into u bounds to make our lives a little bit easier. So the 0 x bound becomes a 1 u bound, and the 1 x bound becomes a 9 x bound. And now we just integrate and evaluate. And then we've got our 1/8 here that we'll take back into account. Clean that up a little bit, and we can evaluate from 1 to 9. So we've got a length of 13 over 6. Try another one. The length of the curve. So we've got a y equals, we've got some x bounds there. So our first order of business is going to be to take the derivative of our function. And then we can just stick it into the formula. Clean it up a bit. Let's clean it up a bit more. And we can clean that up a bit more. Wow, this is amazing. Oh, this is great. Now we can take the square root of something squared. Yes, we get to clean it up a bit more. And now that is not difficult to take the antiderivative of and evaluate. So I know I'm going through this really fast because I know you guys know how to integrate. Pause the video if you want to make sure you get all that written down. The most important part, because this is the new information, is learning the setup. Okay, here we have another one. We've got some x bounds. We have a function in terms of x. So we'll take the derivative, plug that into our formula. So here's my x bounds. I've got the square root of 1 plus the derivative of the function squared. And just plug it into the calculator and you're done. 7.28937. Couple more. Find the length of the curve y equals ln cosine x between 0 and pi over 4. So same thing as before, but we have to use the chain rule. So the derivative of the natural log is 1 over whatever that function is. So 1 over cosine x times the derivative of cosine x, which is negative sine x. Okay, so we've got that part. Y prime equals negative sine x over cosine x, which is just negative tangent x. All right. So here's our formula again. We're going from 0 to pi over 4, the square root of 1 plus the derivative of the function squared dx for a volume of 0.88137. Last one, but notice this time we've got some y bounds. So first thing we're going to have to do is rearrange our function so that it's in terms of y. So we have x equals y to the 3/2, and using the power rule, we can take the derivative of that and then just plug it in again. Here we've got the square root of 1 plus the derivative of the function squared dy using y bounds. I like arc length. I feel like it's pretty simple and straightforward. So thanks for being here, and I will see you in the next lesson when we start a whole new adventure together.